The night sky holds a secret that could rewrite the entire story of our cosmos. We are taught the universe is expanding, a grand aftermath of the Big Bang. But that might be a cosmic illusion. There is a radical possibility that the universe is not expanding at all, but is instead collapsing from the future. This idea turns our understanding of time and existence inside out. By the end of this journey, you will see the cosmos through a completely new lens, one where the past and future are flipped. We will explore the strange evidence that challenges our standard model, from puzzling tensions in cosmic measurements to the ghostly imprints of previous universes. What if everything you know about the beginning is actually a story about the end? How solid do you believe our cosmic foundations really are? The foundation of modern cosmology rests upon a single, profound observation. In the 1920s, astronomer Edwin Hubble made a discovery that would forever change our place in the universe. He found that the farther away a galaxy is, the faster it appears to be rushing away from us. This relationship, now called Hubble's law, painted a clear picture. The entire cosmos is stretching like dots on an inflating balloon, all moving apart from one another. This was the key evidence for the Big Bang theory, the idea that our universe began from a state of incredible heat and density. The final piece of the puzzle seemed to fall into place decades later with the accidental discovery of the cosmic microwave background. This faint glow filling all of space is the cooled remnant of the universe's fiery birth, the afterglow of the Big Bang itself. For generations, this has been the accepted story, a linear narrative of a universe born and expanding. But what if this entire framework, as elegant as it is built upon a misinterpretation of the evidence? The cracks in this foundation are now beginning to show, starting with the very phenomenon that started it all, the redshift of light. This discrepancy is more than a simple mathematical glitch. It is a deep and growing crisis in cosmology. The Hubble tension is the stubborn gap between two ways of measuring how fast the cosmos is growing. One method looks at the nearby universe using celestial landmarks like pulsating stars called Cepheid variables and the brilliant explosions of supernova. These act as standard candles, their known brightness allowing us to calculate vast distances. This local measurement gives us a specific number for the expansion rate, known as the Hubble constant. But when we look back in time to the infant universe, we get a different answer. The Planck satellite meticulously mapped the cosmic microwave background, the faint echo of the Big Bang. By analyzing the subtle patterns in this ancient light, scientists can predict how the universe should have expanded over billions of years to arrive at its present state. This prediction yields a Hubble constant that is noticeably slower. The two results disagree significantly, and no amount of recalibrating our instruments has made the problem go away. It is as if you measured a tree's growth over the past year and then examined a photograph of its seed, only to find the two stories of its growth do not match. This is not a minor oversight. It suggests that our model of cosmic evolution, the very timeline from the Big Bang to today, might be fundamentally flawed. The tension forces a radical question. What if the redshift of distant galaxies, the very cornerstone of the expanding universe theory, does not mean what we think it means? If the universe is not simply expanding, then the redshift must be a sign of something else entirely. This opens the door to a far more bizarre possibility, one where the arrow of time itself is pointing in the wrong direction. This very assumption that redshift equals velocity is the thread we must now pull. For nearly a century, we have taken the faint reddening of starlight as an undeniable sign that space is stretching. The logic seems impeccable. Just as the siren of an ambulance drops in pitch as it speeds away, the light from a receding galaxy is stretched to longer, redder wavelengths. In an expanding universe, this cosmic Doppler effect is the expected consequence. The fabric of space itself is the thing doing the stretching, carrying galaxies along with it. But what if that interpretation is not the only one, or even the correct one? Alternative ideas, once dismissed as fringe, are gaining new attention in light of the Hubble tension. One possibility is that light simply gets tired. As photons travel across billions of light years, they might interact with the sparse medium of space in a way that causes them to lose energy very slowly over these epic journeys. This energy loss would manifest as a redshift, mimicking the effect of motion without any actual expansion required. Another idea points to the vacuum of space itself. What if empty space is not truly empty, but has subtle properties that can subtly alter the light passing through it, like a vast, faintly tinted medium? If either of these mechanisms, or others we have not yet conceived, contribute to the redshift we observe, then the entire story of an expanding universe begins to unravel. The most direct evidence for the Big Bang would transform into a cosmic mirage. And if the universe is not expanding, then the question becomes, what is it actually doing? To answer that, we must challenge an even deeper assumption, the one-way direction of time itself. The very laws that govern the cosmos seem to hold no preference for past or future. If you were to film the dance of two colliding particles and play the recording in reverse, the physics would look just as valid. The equations of motion, the rules of electromagnetism, even the curved geometry of Einstein's relativity, they all work perfectly well with time flowing backwards. This profound symmetry is a cornerstone of fundamental physics, yet it stands in stark contrast to our daily reality. An egg splatters on the floor, but it never spontaneously reassembles. We remember the past, not the future. This undeniable direction is what we call the arrow of time. So where does it come from? Physicists believe it is not written into the bedrock laws of the universe, but emerges from something else entirely, the overwhelming statistical tendency towards disorder. Think of it like a new deck of cards perfectly ordered by suit and value. Shuffle it just once and it becomes more disordered. Shuffle it 1,000 times and it will never return to that original, pristine state by chance alone. The universe, on its grandest scale, might be following a similar rule. The arrow of time may simply be the universe's natural progression from a highly ordered, improbable state to a vastly more probable, disordered one. This is a crucial distinction. It means the forward march of time we experience is not a fundamental rule of reality, but more like a habit, a trend that emerges from countless interactions. And if that is the case, then the direction of time itself could be a local phenomenon, not a cosmic absolute. What if, from a God's eye view, the universe is fundamentally timeless? This philosophical leap allows us to turn our standard cosmic story on its head. If the laws of physics are indifferent to time's direction, then a universe collapsing from a future state of maximum disorder down to a past state of high order is just as physically possible as our story of expansion from an ordered beginning. The Big Bang would not be the start but the finish. This radical rethinking finds its voice in the work of a physicist who dared to take time symmetry to its ultimate conclusion. This timeless symmetry finds its most elegant expression in the work of a true giant of theoretical physics, Roger Penrose. A Nobel laureate, Penrose proposed a theory so profound it redefines the very concept of an ending. He calls it Conformal Cyclic Cosmology, Imagine not one universe with a single birth and death, but an endless series of cosmic cycles, each one an eon. In the far, far future of our own eon, trillions upon trillions of years from now, the universe will have expanded to such an unimaginable degree that all matter will have decayed. Stars will have long since burned out, black holes will have evaporated through Hawking radiation, and all that will remain is a vast, cold, and incredibly dilute sea of massless particles like photons zipping through an ever-expanding emptiness. In this state, the universe loses all sense of scale. Distances become meaningless because there is nothing left to measure them against. The cosmos becomes smooth, featureless, and timeless. And here is the breathtaking twist. Penrose showed that this desolate, empty future state is mathematically identical to the hot, dense, and smooth singularity we call the Big Bang. The end of one eon becomes the beginning of the next in an infinite cycle of cosmic death and rebirth. There is no definitive start and no final stop, only an eternal transformation. While this is not a collapse in the traditional sense, it completely erases the line between the ultimate fate and the initial condition. The Big Bang is no longer a unique creation event, but simply a phase transition, a cosmic reset button pressed by the universe itself. The profound implication is that our entire cosmic history, from the first stars to the rise of life, is just one chapter in an infinite book. Penrose's theory, coming from the pinnacle of mainstream physics, demonstrates that the linear narrative we hold so dear is not the only game in town. It legitimizes the search for models where time's arrow is not fixed, where the past and future are not what they seem. If the end can become the beginning, then perhaps the flow of time itself is more fluid than we ever dared to believe. This is the moment where we flip the cosmic hourglass. The radical idea is not merely a different kind of expansion, but a complete reversal of the cosmic timeline. What if the Big Bang was not the starting gun of the universe, but the finish line of a previous cycle? In this breathtaking scenario, our universe is not flying apart. It is falling together, collapsing under its own gravity towards a single, ultimate event in the future. From our limited perspective, trapped within the river of time, this grand collapse would look exactly like an expansion. Why? Because if the entire timeline is reversed, our local experience remains unchanged. A cup still shatters when it hits the floor, and we still remember yesterday, not tomorrow. Cause and effect would feel perfectly normal to us, but on the grandest scale, the direction of the cosmos would be inverted. The redshift of distant galaxies, which we interpret as a Doppler effect from runaway expansion, would instead be the signature of this immense gravitational infall. Their light would lose energy as it struggles against the collective gravitational pull of the entire cosmos falling inward, creating the same reddening effect we see. We would be living in the aftermath of a future singularity, mistaking the universe's final act for its first. To even begin to accept this, we must untangle one of the most profound relationships in physics, the intimate connection between time and gravity. Gravity, as Einstein taught us, is not a force in the traditional sense, but the curvature of space-time itself. Massive objects like stars and planets warp the fabric of the cosmos, and this warping dictates how things move, including the flow of time. Time itself runs slower in a stronger gravitational field. This is not a theory, it is a measured fact essential for the GPS in your phone to function correctly. Now scale this idea up to the entire universe. If the cosmos is in a state of global gravitational collapse, then the gravitational potential is not uniform. It changes as we look further out and, crucially, as we look further back in time. In a collapsing universe, the past might have been a state of lower overall gravity. while the future holds the ultimate gravitational well, the final singularity. This gradient in gravity could be the true source of the arrow of time we experience, emerging from the universe's overall trajectory towards a high-gravity future. Our perception of time flowing forward could be a direct consequence of living inside a cosmos that is gravitationally falling towards its own destiny. Einstein's revelation was that gravity is not a pull but a shape. Mass and energy mold the fabric of space-time, creating the curves and wells that guide the motion of planets and light. But this curvature does something even more profound. It warps time itself. Clocks tick slower near a massive object like Earth compared to out in empty space. This gravitational time dilation is a subtle but real effect proven by countless experiments. Now, extend this principle to the entire cosmos. If the universe is collapsing toward a future singularity, that final point represents the deepest gravitational well imaginable. As we look outward into space, which is also backward in time, we would be looking toward regions of progressively weaker overall gravity. This cosmic gradient from a low-gravity past to an ultra-high-gravity future would impose a direction on time. Our relentless experience of moving forward could be an emergent property of living inside this immense gravitational slide. The equations of general relativity, which form the bedrock of modern cosmology, are perfectly symmetric in time. They allow for solutions that describe a universe running in reverse. One of the most fascinating is the concept of a white hole. If a black hole is a region of space-time from which nothing can escape, a white hole is its temporal mirror, a region from which nothing can enter. It is a point of pure eruption. In this view, the Big Bang itself could be interpreted as the ultimate white hole event. Instead of a singularity sucking everything in, it would be a singularity spewing everything out. The entire history of our universe from the first instant to the present day would be the aftermath of this explosive emission from a future collapse. The cosmos would not be flying apart from an initial explosion, but we would be witnessing the outward rush of material from a final, cataclysmic detonation that exists in our future. This is not mere science fiction. It is a mathematically consistent, though deeply strange, solution to Einstein's own equations. It provides a legitimate, if radical, alternative framework, one where the evidence we have collected for an expanding universe could be perfectly reinterpreted as signs of a great cosmic infall. This relentless increase in disorder is the most familiar arrow of time. We see it in a melting ice cube, in the fading heat of a cup of coffee, and in the irreversible shattering of an egg. This is the second law of thermodynamics in action, a fundamental rule stating that entropy, a measure of chaos, always increases in any isolated system. In our standard cosmic story, this law finds its ultimate expression. The universe began in a state of almost impossibly low entropy at the Big Bang, a condition of exquisite and highly improbable order. Everything since has been a long, slow slide into ever greater disorder, a journey that gives our lives a clear direction from past to future. But this beautiful consistency creates a profound puzzle if we dare to flip the cosmic timeline. If the universe is actually collapsing from the future, how can we reconcile our daily experience of increasing mess with a cosmos running in reverse? The answer may lie in a subtle but crucial distinction between our local reality and the universe's global fate. From our perspective, trapped within the flow of time, the second law would still hold sway. Cups would still break and never unbreak because the statistical tendency toward disorder operates perfectly well on a small scale, regardless of the universe's overall direction. The real twist concerns the boundary conditions, the starting and ending points of the entire cosmos. In the Standard Model, the universe starts with low entropy and ends with maximum entropy, a featureless heat death. But in the Collapsing Model, this sequence is inverted. The ultimate fate of the universe, what we call the far future, would actually be the state of highest entropy, a vast, cold, and perfectly disordered expanse. The Big Bang, then, would not be the beginning of low entropy, but the final destination. It would be the moment of ultimate order, the singularity toward which the entire cosmos is collapsing. This turns cosmology on its head. The great mystery of why the universe began in such a special, low-entropy state vanishes. Instead, the low-entropy Big Bang is not an initial condition to be explained, but a final condition, an attractor state that the universe is inevitably drawn toward. The arrow of time we feel, the increase of entropy in our lives, would be a local manifestation of the universe's global journey from a disordered future to an ordered past. We are not emerging from order into chaos, but are instead carried along by a cosmos that is falling into order. This radical redefinition of beginnings and endings forces us to confront the ultimate question of cosmic origins. If the Big Bang is a final state, then what or who set the universe on this path of collapse in the first place? The orderly collapse into a low-entropy Big Bang presents a puzzle of cosmic proportions. Who or what lays down the rails for this entire journey? The answer might lie in the most counterintuitive realm of physics, the quantum world. Here, our everyday logic breaks down, and with it, our rigid understanding of cause and effect. In the strange domain of particles, the future might not be a blank slate waiting to be written, but an active participant in shaping the present. This idea is known as Retro-Causality. One of the most compelling frameworks for it is called the transactional interpretation of quantum mechanics. Forget particles for a moment. Think of a quantum event, like an electron deciding which path to take, as a kind of handshake. An alpha wave travels forward in time from the past, proposing a range of possibilities. But then, a confirmation wave travels backward in time from the future, selecting which one of those possibilities actually becomes real. The event is only settled once this two-way communication is complete. The future outcome reaches back and confirms its own cause. Now, scale this dizzying concept up to the entire universe. If the final state of the cosmos, the Big Bang singularity, is a fixed and inevitable destination, it could be sending confirmation waves backward through all of time. Every quantum event in the history of the universe, from the formation of the first atoms to the nuclear reactions inside stars, would be subtly guided by this ultimate future goal. The entire cosmic timeline becomes a self-consistent loop, perfectly arranged to ensure it arrives at its own beginning. This is not magic, it is a potential consequence of the laws that govern the very small. While speculative, it provides a mechanism that makes the collapsing universe model more than just a philosophical flip. It suggests that the eerie fine-tuning of the universe's constants, the precise values that allow for galaxies, planets, and life, might not be a bizarre accident. They could be the necessary prerequisites, etched into reality from the future, to guarantee the cosmos completes its singular loop. If the universe is indeed a closed time-like curve on a grand scale, it must leave behind echoes of its strange geometry. The search for these cosmic fingerprints leads us back to the oldest photograph ever taken, the cosmic microwave background. This faint glow is the ultimate snapshot of the infant universe, a baby picture from when the cosmos was just 380,000 years old. In the Standard Model, this background should be almost perfectly smooth, with only tiny, random fluctuations seeded by quantum processes during a brief period of hyper-fast expansion called inflation. But if the universe has a more complex history, if it is cyclical or its timeline is reversed, this ancient light might bear scars from events that should not exist. Roger Penrose and his collaborators have made a bold claim. They argue that deep within the CMB data, there are strange, circular patterns of temperature variation, regions that are slightly warmer or cooler than their surroundings. These are not the random blips predicted by inflation, but concentric rings like ripples on a pond. Penrose calls them Hawking points. His hypothesis is as staggering as it is simple. These rings could be the final, fading emission from supermassive black holes that evaporated at the end of a previous cosmic cycle, an eon that existed before our Big Bang. In his Conformal Cyclic Cosmology, the death throes of these colossal objects, their Hawking radiation, could have been imprinted onto the fabric of spacetime itself, surviving the transition from one eon to the next and manifesting as subtle anomalies in our universe's first light. It is a claim that, if verified, would be the first direct evidence of a universe that existed before our own. The scientific community remains deeply divided. Critics argue these features could be statistical flukes, patterns our brains are fooled into seeing in random noise. Yet the very possibility pushes our observational tools to their limits, challenging us to look deeper. A collapsing universe model would predict its own unique signature in this cosmic background. Instead of the generally uniform distribution of hot and cold spots we expect, a cosmos falling inward from a future state might show a specific kind of large-scale asymmetry, a preferred direction or alignment in the temperature fluctuations. It would be like finding a hidden watermark on the universe's birth certificate, a pattern that only makes sense if the document was actually signed in the future. Current and future missions, like the European Space Agency's Planck satellite and its successors, are meticulously analyzing this ancient light, searching for any deviation from the standard story. The hunt for these anomalies is a high-stakes game, one that could either lock in our current understanding of cosmic history or tear it down completely, revealing a universe that is far stranger and more interconnected than we ever dreamed. The most mysterious ingredient in our cosmic recipe is dark energy. In the standard expanding model, it is the enigmatic force responsible for a baffling discovery made in the late 1990s. Astronomers found that not only is the universe expanding, but the expansion is also speeding up. Galaxies are flying apart faster and faster, as if pushed by some invisible, repulsive energy inherent to the fabric of space itself. This dark energy constitutes about 70% of the universe's total energy budget, yet we have no idea what it is. Its observed strength is bafflingly weak, a decimal point followed by 120 zeros smaller than what our best theories of the quantum world predict. This colossal mismatch is known as the cosmological constant problem, and it is arguably the most profound failure of theoretical physics. But what if this problem is a mirage created by a flawed assumption about time's direction? In a universe collapsing from the future, dark energy would not be a force of repulsion. It would be something else entirely, perhaps the subtle pull of the ultimate destination. Imagine you are in a boat on a wide, slow-moving river, drifting toward a massive waterfall far in the distance. You cannot see the waterfall yet, but you can feel its influence. The current begins to pick up speed the closer you get. From your perspective on the boat, it feels as if an invisible force is pushing you forward, accelerating your journey. But in reality, you are being pulled by the immense gravitational attraction of the waterfall ahead. In the collapsing cosmos model, dark energy could be the cosmic equivalent of that accelerating current. It is not a mysterious anti-gravity push, but the growing gravitational influence of the future Big Bang singularity. The universe is not blowing up, it is winding down, falling inward, and what we measure as an accelerating expansion is actually the increasing momentum of that grand cosmic infall. This reinterpretation could elegantly dissolve the cosmological constant problem. The vacuum energy predicted by quantum theory might still be there, but its gravitational effect is not to push the universe apart. Instead, its role is woven into the overall geometry of a spacetime that is destined to collapse. The puzzling weakness of dark energy's observed effect would no longer be a problem of missing physics, but a consequence of us misreading the universe's ultimate trajectory. The question shifts from why is this force so strangely weak and repulsive, to why is the pull of the final state exactly as strong as we observe. This flipped perspective turns one of cosmology's greatest mysteries into a potentially solvable feature of a cyclical or time-symmetric universe. Black holes, the ultimate symbols of cosmic finality, would have their entire purpose rewritten in a collapsing universe. In our current timeline, they are endpoints, gravitational traps from which nothing, not even light, can escape. They form from the corpses of massive stars and slowly, over trillions of years, evaporate into nothingness through a faint quantum process called Hawking radiation. Their story is one of consumption and a slow, quiet fade. But if the cosmos is falling inward from the future, this narrative is turned on its head. As the universe contracts, galaxies would be drawn closer together. In this cosmic traffic jam, the supermassive black holes at their centers would have far more opportunities to collide and merge. Instead of isolated monsters drifting apart in an expanding void, they would coalesce, growing into ever more colossal singularities. The universe would not be scattering its dark hearts to the wind, but gathering them, concentrating gravitational power as it marches toward its ultimate destiny. This is only one possibility, and the other is even more mind-bending. If the arrow of time is globally reversed, then the very definition of a black hole could invert. From our forward-moving perspective, a black hole is a one-way street into oblivion. But from the reversed viewpoint of the cosmos as a whole, that same object might appear as its exact opposite, a white hole. A white hole is a theoretical region of spacetime from which matter and energy can only pour out. Nothing can enter. It would be a fountain of creation, not a drain of destruction. In this flipped timeline, the black holes we observe would be white holes in disguise. Their event horizons would not be points of no return, but the birth canals for the universe's contents. The matter and energy we see them consuming today would, from the reversed cosmic perspective, actually be the final stages of their emission. A black hole devouring a star would look, to a time-reversed observer, like a white hole giving birth to one. This transforms black holes from grim reapers into cosmic midwives. Their entire life cycle is played in reverse. Their slow evaporation via Hawking radiation becomes, in the collapsing model, the process of their formation. The faint glow of their demise is instead the gathering of their substance. They would be the engines that reassemble the dispersed energy of the universe, funneling it back toward the singular state of the Big Bang. Their behavior becomes a critical test for this radical cosmology. Astronomers are already studying the final moments of black hole mergers through the gravitational waves they produce, ripples in spacetime. In a collapsing universe, the pattern and properties of these waves might carry a subtle signature of time reversal, a hint that we are witnessing not a collision toward silence, but a unification toward a new beginning. The silent, dark voids we fear could be the very mechanisms of cosmic rebirth. This paradox strikes at the very heart of our understanding of reality, pitting two pillars of modern physics against each other. Quantum mechanics, the rules governing the very small, holds a sacred principle. Information is never truly lost. Every detail about a particle, its properties, its history, must be preserved in some form. It can be scrambled like an egg, but it can never be erased from the universe's ledger. General relativity, which describes gravity and the large-scale structure of spacetime, tells a different story. When matter crosses the event horizon of a black hole, it is thought to be crushed into a singularity, a point of infinite density where the known laws of physics break down. According to this view, all information about that matter is irretrievably destroyed. This is the black hole information paradox, a conflict that has troubled physicists for decades. But what if the paradox is not a flaw in the laws of physics, but a flaw in our cosmic narrative? If the universe is a closed loop collapsing from the future, the idea of permanent loss becomes meaningless. In a truly cyclic cosmos, there is no final evaporation, no ultimate disappearance. The information swallowed by a black hole would not be erased. Instead, it would be processed, transformed, and ultimately incorporated into the structure of the final singularity, which is itself the Big Bang of the next cycle. It is not lost but recycled. Imagine a library where every book ever written is eventually fed into a giant shredder. In our standard linear model, this is a tragedy of lost knowledge. But in the cyclic model, the shredded paper is not thrown away. It is pulped, pressed, and becomes the very pages for a new set of books containing all the same information, just in a different, more fundamental form. The information is preserved in the fabric of the cosmos itself, waiting to be expressed again in the next cosmic iteration. The paradox vanishes when we let go of the idea of a definitive end. The information was never in danger. It was just on a journey through time that is far grander and more interconnected than we had supposed. These profound objections cannot be dismissed lightly, standing as formidable barriers to this radical reimagining of the cosmos. The standard model of cosmology, for all its tensions, provides a remarkably coherent story that explains a vast collection of independent observations. The collapse hypothesis must face this evidence head-on. Consider the origin of the universe's lightest elements. The observed cosmic abundances of hydrogen, helium, and lithium match the predictions of Big Bang nucleosynthesis with stunning precision. This process, which occurred in the first few minutes of a hot, dense, expanding universe, is a cornerstone of our understanding. A collapsing model must offer an equally compelling explanation for why these exact ratios exist, perhaps by proposing that the intense pressures and temperatures of a final collapse somehow mimic the conditions of a beginning. Similarly, the intricate pattern of hot and cold spots in the cosmic microwave background has been mapped in exquisite detail. The standard model, with its period of rapid inflation, explains the statistical distribution of these fluctuations almost perfectly. Any alternative theory must account for this specific, observed structure without relying on an inflationary epoch, a monumental task that currently leaves the collapsing universe idea at a significant disadvantage. Beyond the observational hurdles lie even deeper conceptual problems. The idea of a globally reversed arrow of time creates a paradox at the heart of causality itself. If the universe is collapsing from the future, then every effect we perceive would, from the cosmic perspective, have its cause in the future. A supernova explosion would be caused by the collapse of the universe that happens billions of years later. This turns our fundamental understanding of how events unfold inside out. Why then does our local experience feel so perfectly consistent? Why do we remember the past and not the future? Why does cause always precede effect in every experiment we have ever conducted? Proponents of the model argue that our local arrow of time is an emergent property, dictated by the increase of entropy in our immediate environment. This local trend could operate independently of the universe's global direction, like a leaf floating down a stream that is itself flowing upstream. we would be carried along by the local current of time, unaware of the river's contrary overall flow. It is a clever argument, but it stretches the idea of emergence to its absolute limit, requiring a clean separation between our reality and the cosmos that seems almost too convenient. The ultimate challenge is one of simplicity. The standard model, with its single beginning and forward-moving expansion, is intuitively straightforward, even if it leaves some mysteries unanswered. The collapsing universe model, by comparison, appears convoluted, introducing layers of philosophical complexity to solve problems that might have more conventional solutions. It asks us to accept a cosmic-scale reversal of time to explain redshift, while simultaneously inventing new mechanisms to explain everything else the standard model already handles well. For many scientists, this is a step too far, a case of the cure being more radical than the disease. Yet, the very existence of these profound criticisms is what makes the exploration so vital. It forces us to question the bedrock assumptions of cosmology, to ask if the evidence we see could possibly be interpreted in another way. The tension between a simple, elegant story and a strange, counterintuitive one is the engine of scientific progress. Perhaps the true value of this idea is not in being right, but in compelling us to look at the universe with fresh eyes, to wonder if the story we tell ourselves about time and existence is the only one that can be written. This cosmic loop erases the very distinction between a beginning and an end. We are left with a universe that simply is a complete and timeless object. This view, known as eternalism, proposes that the past, present, and future are not sequential. They all exist simultaneously, laid out across the expanse of space-time like frames on a strip of film. The Big Bang is not a moment that happened long ago. It is a location in this four-dimensional structure. The heat-death of the universe is not a distant fate, but another fixed point. In this static block universe, our vivid, flowing sense of the present, the feeling that the now is special and constantly moving forward, becomes a powerful illusion generated by our consciousness. We are like a reader progressing through a book, page by page, experiencing the story linearly even though every chapter already exists, complete and unchanging, between the covers. If the future is as real as the past, then the choices we believe we are making are, in a sense, already made. The entire trajectory of your life, from your first breath to your last, is a single, unchanging shape in the cosmic block. This seems to strike a fatal blow to our concept of free will. How can we be free agents if our future actions are just as fixed as our past ones? Yet, perhaps this is a misunderstanding. Your choices are still your choices. Your thoughts are still your thoughts. They are simply part of the eternal fabric of the cosmos. The feeling of making a decision is no less real because the outcome is part of a larger, predetermined structure. The block universe does not invalidate your experience, it just recontextualizes it on a cosmic scale. This perspective transforms the meaning of existence itself. In the standard story, we are temporary accidents in a universe rushing toward emptiness. But in the collapsing model, our lives are integral threads woven into a cosmic tapestry that has no true start or finish. The universe is not a one-act play with a tragic ending, but an infinite loop where every part is necessary for the whole. Your consciousness, your brief moment of awareness, is not a fleeting spark in the dark. It is a permanent feature of reality, a necessary point of view within the eternal block. The ultimate question shifts from why are we here to what does it mean that we have always been here and always will be as part of a universe that is complete and self-contained. Our journey through a collapsing cosmos is a radical path, but it is not the only alternative roadmap. Other theories also seek to escape the singularity of the Big Bang, offering different visions of cosmic rebirth. One of the most enduring is the idea of the Big Bounce. Imagine a universe that breathes. Instead of a single explosive birth, it undergoes an endless cycle of expansion and contraction. After trillions of years of flying apart, gravity finally wins the tug of war, pulling all matter and energy back together into a fiery crunch. This crunch does not mark an end but a rebound. The immense energy and density fuel a new Big Bang, and the cycle begins again. It is a cosmic heartbeat, a universe with no true beginning and no final end. This model shares the cyclic nature of Penrose's Conformal Cyclic Cosmology, but operates within a more traditional flow of time. The universe expands, contracts, and bounces, all while time moves forward in each cycle. The challenge for the Big Bounce lies in the physics of the bounce itself. Can a collapsing universe rebound without simply forming a black hole that swallows everything? Some theories suggest a quantum repulsion at ultra-high densities could provide the necessary push, but this remains a speculative frontier of physics. Then there is the theory of eternal inflation, which paints a picture of a multiverse so vast it defies comprehension. In this view, the vacuum of space possesses a strange, repulsive energy that drives exponential expansion. Our entire observable universe is just one bubble that formed when this energy decayed in a local region, creating a hot Big Bang. But outside our bubble, the inflationary energy remains, spawning new bubble universes endlessly. Our cosmos is not a lone island, but one frothy bubble in a cosmic sea that is eternally boiling with new universes, each with potentially different physical laws. This model sidesteps the question of a singular beginning altogether. There was no first bubble, just an eternal process of creation. The strength of eternal inflation is its ability to explain the strange fine-tuning of our universe. If an infinite number of bubbles exist, then a bubble with laws just right for life, like ours, becomes a statistical certainty. Its primary weakness is its untestability. By definition, these other universes are beyond our causal horizon, forever hidden from observation. Placing the collapse from the future model alongside these ideas reveals a fascinating spectrum of thought. The Big Bounce offers a cyclic universe within a single timeline. Eternal inflation offers a linear but endless creation of new timelines. The collapsing model is unique, proposing a cyclic universe built upon a reversal of time itself. Each theory attempts to solve the puzzles of our origin in its own way. The Big Bounce elegantly avoids a definitive beginning. Eternal inflation uses the multiverse to explain our universe's unlikely properties. The collapsing model directly addresses the strange nature of time and the Hubble tension by reinterpreting our most basic observations. Their weaknesses are equally revealing. The bounce mechanism is unproven. The multiverse may be forever beyond science, and the time-reversed cosmos challenges our most fundamental experience of reality. This landscape of ideas shows that cosmology is far from a settled field. It is a vibrant, sometimes contentious, exploration of the deepest questions, where the evidence we have can be woven into several profoundly different, yet mathematically possible stories. The true shape of cosmic history remains the ultimate mystery, waiting for a decisive clue to point the way. This intimate link between time and awareness pushes us into the most speculative territory yet. If the universe's timeline is truly inverted, then our own conscious experience, the very feeling of a present moment moving forward, might not be a mere accident. It could be a fundamental feature of the cosmos itself. Some thinkers propose that the arrow of time is not just a product of thermodynamics, but is intrinsically tied to the way conscious minds process information. We do not simply witness the flow of time, we generate it through the act of perception. our brains are constantly taking a chaotic stream of sensory data and assembling it into a coherent, linear narrative. This act of creating an ordered past from a disordered present might be the very engine that drives our local experience of time's arrow. In this view, consciousness is not a passive observer of a pre-existing timeline, but an active participant in its construction. The universe provides the raw, timeless data, and our minds stitch it into the story of a flowing present. This idea ventures into the philosophical realm of panpsychism, which suggests that consciousness is not a unique product of complex brains, but a fundamental property of the universe, much like mass or charge. Even the most basic particles might possess a faint, elemental form of experience. If that is true, then the cosmos is not a cold, empty machine. It is a vast, experiencing entity. The grand arrow of time we measure in the redshift of galaxies and the fading of stars could be the macroscopic expression of countless tiny arrows of perception, all aligned by the universe's overall trajectory. Our own deep-seated feeling that time flows in one direction would then be a direct reflection of the cosmos's journey from a disordered future to an ordered past. We are not just living inside this collapsing universe, we are expressions of its fundamental nature. This leads to a staggering possibility. Could it be that conscious observers like us can only emerge during a specific phase of the cosmic cycle? Perhaps a universe needs to have a clear, dominant arrow of time, a consistent flow from order to disorder or vice versa, to create the stable conditions necessary for complex information processing. In a timeless, perfectly balanced state, like the featureless void at the far end of a cycle, consciousness might be impossible. We exist because the universe is on a journey, and our minds are the instruments it uses to experience that journey. This is not mainstream science, but a profound philosophical implication. It suggests that we are not accidental tourists in a meaningless expanse. We are an integral part of the universe's temporal architecture, the means by which the cosmos knows itself. The mystery of why we perceive a flowing time might be the same mystery as why the universe has a direction at all. The true test of any cosmic theory lies not in its elegance but in its predictions. Our current telescopes and satellites have brought us to the precipice of a revolution, but the final leap will require a new generation of eyes on the sky. These instruments, now in operation or on the drawing board, are designed to probe the deepest mysteries of the cosmos, and in doing so, they may accidentally stumble upon evidence for a timeline running in reverse. The James Webb Space Telescope is already rewriting the first chapters of galactic history. By gazing at the most distant and therefore earliest galaxies, it has found something perplexing. Some of these infant star systems appear unexpectedly massive and mature, as if they had more time to evolve than the standard model allows. In an expanding universe timeline, this is a serious anomaly. But in a collapsing model, our perspective is flipped. What we see as the early universe might actually be much closer to the final, mature state of the previous cycle. Those surprisingly well-developed galaxies would not be premature, but rather exactly what we should expect to see if we are looking backward toward a cosmic old age. This is just the beginning. Future missions dedicated to the cosmic microwave background will map its subtle temperature variations with even greater precision. If concentric rings or Hawking points truly exist as scars from a prior eon, these advanced observatories will find them. Their discovery would be a monumental shift, providing tangible evidence of a universe that existed before our own. Conversely, if no such patterns emerge after exhaustive searching, it would be a significant blow to cyclical models. Then there is the new science of listening to the cosmos. Gravitational wave observatories like LIGO and Virgo are tuning their ears to the ripples in space-time caused by cataclysmic events. As they detect more black hole mergers from different epochs, a peculiar signature might emerge. The gravitational waves from these collisions carry information about the expansion history of the universe. If that history is not a simple, smooth expansion but a complex infall, the data might reveal inconsistencies, a subtle distortion in the signal that the standard model cannot account for. The ultimate goal is to find a smoking gun, a single piece of evidence that definitively supports the collapsing universe idea, while being impossible to explain within the current paradigm. Imagine if we detected a clear, statistical asymmetry in the cosmic microwave background, a specific kind of alignment that points toward a particular direction in space, a preferred axis that should not exist in an isotropic, expanding universe. Such a finding would shatter the foundational principle of cosmological homogeneity and force us to consider that we are living within a dynamic flow, a cosmic current pulling us toward a singular destiny. The next decade of astronomical discovery will be a high-stakes interrogation of the cosmos, and the answers we get may be far stranger than the questions we are asking. This search for our universe's singular story inevitably opens a door to an even grander possibility. The idea of a multiverse, a vast collection of parallel realities, is no longer confined to science fiction. It has become a serious, though speculative, consideration for cosmologists grappling with the strange coincidences in our own cosmic home. Our universe seems suspiciously well suited for life. The fundamental forces are balanced on a knife's edge. If the strength of gravity were even slightly different, stars would not form or would burn out too quickly. If the nuclear forces were weaker, complex atoms could never exist. This apparent fine-tuning is one of the deepest puzzles in physics. In a multiverse, this puzzle finds a potential answer through the Anthropic Principle. The reasoning is simple yet profound. If an infinite number of universes exist, each with its own random set of physical laws and constants, then it is no surprise that we find ourselves in one of the rare universes where those laws permit our existence. We could not possibly observe a universe that was hostile to life. This logic shifts the question from why is our universe so special to what are the statistical rules that govern the multiverse. It is within this vast landscape that the collapsing universe model finds a new and intriguing home. Perhaps our cosmos is not the standard model. What if most universes in the multiverse do indeed follow the familiar pattern of expansion from a Big Bang? But in such an immense ensemble, every possible cosmic history must play out somewhere. There could be universes that are forever static, others that collapse immediately, and some, like the one we might be living in, that are caught in a strange, time-reversed loop. Our universe would not be a replacement for the entire cosmological rulebook, but a fascinating exception. It would be a special case, a unique solution to the equations of physics that occurs under very specific conditions. This perspective makes the hypothesis far more palatable. Instead of demanding that we throw out all of established cosmology, it suggests that our reality is simply one particular thread in a tapestry of unimaginable variety. The multiverse becomes the ultimate laboratory, a cosmic arena where every possible narrative, no matter how counterintuitive, is being written. The accelerating expansion we call dark energy, the stubborn Hubble tension, even the eerie silence of the cosmos, could all be local features of our particular cosmic neighborhood. We are not studying the universe in isolation, but are instead examining a single specimen from an infinite collection. This realization does not make the mystery smaller, but infinitely larger, inviting us to consider that the true nature of reality extends far beyond the horizon of our own expanding, or perhaps collapsing, sky. A major puzzle has always lurked at the very heart of the Big Bang theory. a question so profound that standard cosmology can only shrug its shoulders. Why did the universe begin in such an incredibly specific and improbable state? The cosmos we see today is messy and disordered, filled with scattered galaxies and the fading energy of dying stars. Yet all evidence points to the fact that it started in a condition of almost impossibly low entropy, a state of exquisite and finely tuned order. This is the problem of initial conditions. It is the cosmic version of walking into a room after an explosion and finding that every single piece of dust has settled into a perfect, intricate mosaic on the floor. The standard model offers no reason for this. It simply posits that the universe started this way, treating this special beginning as a mysterious boundary condition, a given fact that we must accept without explanation. It is the ultimate free parameter in our equations, an arbitrary starting point that begs the question of what or who set the dials with such precision. This is where the collapsing universe model turns the problem inside out, offering a potential solution that is as elegant as it is radical. If the Big Bang is not the beginning but the end, then the low entropy state is no longer an arbitrary initial condition. It becomes the natural, inevitable destination of the entire cosmic journey. The universe is not emerging from order into chaos, but is instead collapsing from a future state of maximum disorder down into a final state of ultimate order. The exquisite fine-tuning of the Big Bang is transformed from a mysterious starting pistol into a gravitational attractor, a point towards which the entire cosmos is irresistibly drawn. The question shifts from why did the universe start this way to why is it destined to end this way? And that is a question that physics might actually be able to answer, perhaps through the gravitational dynamics of a closed universe or the quantum properties of a final singularity. This reframing dissolves the need for a cosmic architect to carefully choose the universe's starting settings. The order we see at the Big Bang is not a gift from outside the system, but a dynamical result generated by the system's own evolution. It turns a baffling boundary mystery into a feature of the cosmic story itself. Long before telescopes or quantum equations, humanity looked to the heavens and saw a story of eternal return. The ancient sages of India described a cosmos breathing in vast cycles called kalpas, periods of creation and dissolution that span billions of years. In these cycles, the universe is not born and then fades away, but is continuously reborn, with each ending giving rise to a new beginning. The ancient Greeks, too, pondered a cyclical nature of time, with the Stoic philosophers teaching of a great year, after which the cosmos would be consumed by fire and then renewed, repeating the same events for eternity. These are not isolated ideas. From the Norse myth of Ragnarok, a destruction that precedes a fertile new world, to the recurring cycles in Mayan and Buddhist traditions, a common thread emerges. Human culture is rich with the intuition that time is not a one-way street. The scientific hypothesis of a universe collapsing from the future is not arriving in a vacuum. It is the latest chapter in an ancient human conversation about the shape of eternity. It resonates with a deep-seated feeling that the cosmos operates on a grand, rhythmic scale, where death is always a prelude to rebirth. This is more than a curious coincidence. It suggests that the human mind, through myth and reason, has been circling a profound truth about reality. Science, with its precise measurements and mathematical rigor, and mythology, with its symbolic narratives and intuitive wisdom, are two different languages describing the same cosmic mystery. One uses data, the other uses story, but both are attempts to answer the fundamental questions of where we came from and where we are going. When our most advanced theories begin to echo our oldest stories, it is a powerful reminder that our quest for understanding is a continuous thread woven through the entirety of human history. The idea that the end is the beginning is not a radical new thought, but perhaps the recovery of a very old one, now dressed in the equations of general relativity and the data of space telescopes. This question of a predetermined cosmos touches the very core of our moral lives. If the future is a fixed point toward which we are inevitably falling, then every choice we believe we are making, from the profound to the trivial, might be an illusion. It is a terrifying thought, one that seems to drain our struggles and triumphs of all their significance. Why strive for justice? Why show compassion? Why create art if the script has already been written? This is the ancient philosophical specter of determinism, and the collapsing universe model gives it a powerful, cosmic form. Yet, this fear may rest on a misunderstanding of what it means for something to be real. Imagine a novel you love. Every event in the story, every word spoken by the characters is fixed on the page. The ending is predetermined. Yet, as you read, the characters' choices feel real and consequential. Their joys and sorrows matter within the context of the narrative. Your experience of their journey is not diminished by the fact that the author completed the book long ago. In the same way, our lives could be seen as a story written into the fabric of a four-dimensional universe. The fact that the entire timeline exists as a complete object does not negate the reality of our experience within it. Your feeling of making a difficult decision, the weight of moral responsibility, the joy of a hard-won success, these are the very substance of the cosmic story. They are not illusions, they are the necessary components that make the timeline what it is. Our actions are still the causes that bring about the effects we see around us. Your kindness is still the reason for another's smile. Your hard work is still the reason for your achievement, regardless of the universe's ultimate geometry. The ethical dimension, then, does not fade away, it is simply reframed. The importance of our actions is not lessened by a fixed future, it is woven into the eternal structure of reality itself. This perspective adds a profound layer of cosmic poignancy to our existence. We are not temporary accidents in a meaningless void, but integral participants in a grand, self-consistent narrative. The universe did not just permit life and agency by chance, it necessitated them as essential elements of its own complete and timeless form. Our brief, conscious moment is not a flicker in the dark, but a permanent and indispensable line in the cosmic script. Another modern lens for this cosmic reversal comes from the world of computers and the provocative simulation hypothesis. This idea suggests that our entire reality, from the smallest particle to the largest galaxy, might be an incredibly sophisticated digital construction. In such a simulation, the arrow of time we experience would not be a fundamental feature of the hardware, but an emergent property of the software. It is simply the order in which the program processes information. Think of watching a movie file on your computer. The narrative unfolds from beginning to end, a clear and irreversible sequence of events. Yet, the data comprising that movie exists all at once on the hard drive. You could just as easily instruct the media player to run the film in reverse. The underlying information is unchanged, but the experienced timeline is completely inverted. Apply this analogy to the cosmos. What if the universe's underlying code describes a process of gravitational collapse from a future singularity? The program's fundamental instructions dictate that everything is moving toward a single point. Yet, for us, the simulated observers within the program, the output is rendered as an expanding universe. The redshift of galaxies and the apparent acceleration we measure would be the visual and mathematical results of this rendering process. a user interface that makes the collapse comprehensible to beings living inside it. In this view, the laws of physics are not immutable truths etched into the fabric of space, but the operating rules of the simulation, the algorithms that govern how energy, matter, and information interact. The strange puzzles of quantum mechanics, where particles seem to be in multiple states at once until observed, could be seen as processing optimizations, a way for the cosmic computer to save resources by only calculating precise properties when needed. This perspective does not prove we are living in a simulation, but it provides a powerful and relatable framework for understanding how a reality with a reversed global timeline could function. It links the deepest questions of fundamental physics to the principles of information theory, suggesting that the universe's most mysterious behaviors might be features of a system processing data according to a hidden, and perhaps inverted, script. Both models of the cosmos, the expanding and the collapsing, ultimately confront the same terrifying wall, the singularity. It is a word that signifies a complete surrender of our understanding, a point of infinite density and temperature where the known laws of physics simply cease to function. In the standard story, this is the moment of the Big Bang itself, a fiery birth from a state we cannot describe. In the collapsing model, it is the grand finale, the future destination toward which all of reality is falling. An infinite density is not a physical concept we can work with. It is a mathematical warning sign that our theories are incomplete. The true hope for resolving this impasse lies not in choosing one timeline over another, but in a deeper theory that transcends both. Physicists call this the quest for quantum gravity, a framework that would marry the rules of the very small, quantum mechanics, with the rules of the very large, general relativity. In this hoped-for theory, singularities would not be real. They would be illusions, placeholders for a process we do not yet understand. Theories like string theory or loop quantum gravity suggest that at these extreme scales, the fabric of spacetime itself might be granular, woven from tiny loops or vibrating strings. This fundamental graininess would prevent density from ever reaching a true infinity. Instead of a catastrophic singularity, there would be a supremely dense but finite state where quantum effects take over. For a universe collapsing from the future, this changes everything. The Big Bang would no longer be a mysterious beginning or a grim end. It would be a quantum bounce. The immense gravitational pressure of the collapse would not crush everything into nothingness, but would instead trigger a phase transition, like water freezing into ice or steam condensing into liquid. The universe would reach a maximum density and then rebound, smoothly transitioning into a new state of expansion. In this view, the collapsing model does not so much solve the singularity problem as it reframes it. The initial singularity of the standard model is transformed. It becomes the quantum gravitational event that marks the turning point from a prior cycle of collapse into our current phase of what we perceive as expansion. The mystery of the beginning is replaced by the physics of a transition. This shifts the greatest question of cosmology from why was there a beginning to what are the laws that govern the transformation from one cosmic state to another. The search for quantum gravity is therefore not an abstract exercise. It is the search for the engine of cosmic rebirth, the mechanism that could make an eternal, cyclical universe physically possible. This very strangeness leads to a profound question about our own place in the cosmic story. Why do we, as conscious observers, find ourselves here and now, in this seemingly stable epoch of cosmic history? The Anthropic Principle offers a compelling, if humbling, perspective. It suggests that the universe we observe must be compatible with our existence as observers. We could not possibly find ourselves in a universe or a phase of a universe that is hostile to the development of life. In a collapsing cosmos, this principle takes on a fascinating new dimension. If the universe is truly falling inward from the future, then the conditions necessary for life must emerge somewhere along that timeline. The phase we call the present, which we interpret as an expansion, is likely the only window in the entire cosmic cycle that is both long enough and stable enough for the intricate dance of complexity to unfold. Consider the requirements. It takes billions of years for gravity to gather primordial hydrogen and helium into vast galaxies. It takes more billions of years for generations of stars to forge the heavier elements like carbon and oxygen in their nuclear furnaces, and then scatter them across space in supernova explosions. Only then can new stars form, encircled by planets rich with the chemistry of life. This entire process demands an immense stretch of cosmic time where temperatures are moderate, energies are not too extreme, and the fabric of spacetime is relatively calm. In the fiery chaos near the final singularity, or in the cold, diluted emptiness of the far future, such stable conditions would be impossible. The Anthropic Principle, therefore, acts as a powerful filter. It explains why our conscious observation is necessarily anchored to this specific era. We are not witnessing the universe's youth in a traditional sense, but rather its most fertile and hospitable period, a golden age nestled within a much grander and more alien cycle. Our very existence becomes the strongest evidence that this phase is special, not necessarily because it is the beginning, but because it is the only part of the story where beings like us can arise to read the cosmic script. This realization does not make our time less significant. It frames our brief moment of awareness as a necessary feature of a cosmos that is, in its own strange way, fine-tuned for observation. This grand quest for a final theory is the ultimate challenge in physics. For decades, the greatest minds have struggled to unite the two pillars of modern science, general relativity and quantum mechanics. One describes the universe on its largest scales, the warping of spacetime by stars and galaxies. The other governs the bizarre world of atoms and particles. Both are spectacularly successful in their own domains, but they are built on foundations that seem fundamentally incompatible. The most profound rift between them concerns the nature of time itself. In Einstein's relativity, time is woven into a flexible, four-dimensional fabric. It is dynamic, it can curve and stretch, but it is a continuous and smooth backdrop for events. In the quantum realm, time is treated as an absolute, external parameter, a rigid stage upon which particles dance. It does not fluctuate or interact. This is more than a philosophical disagreement. It is a mathematical chasm that prevents us from describing the earliest moments of the Big Bang or the interior of a black hole, places where both gravity and quantum effects must be paramount. A cosmological model that dares to reinterpret the arrow of time on a cosmic scale does not just offer an alternative history, it could provide the crucial bridge across this divide. By proposing that the global flow of time is not a fixed background but an emergent property of the universe's overall state, it reframes the entire problem. Suddenly, time is no longer a given but a variable to be explained. This shift in perspective is exactly what might be needed to find a common language between the two theories. Imagine trying to merge two maps of the same city that were drawn with different north arrows. The streets will never line up, but if you realize that north itself is not fixed, that the maps were drawn from moving perspectives, a new way to align them appears. The collapsing universe idea acts as that realization. It suggests that the conflict between quantum mechanics and general relativity over time might stem from our mistaken assumption about the universe's fundamental direction. If we are living inside a cosmic process that is globally running in reverse from our local perspective, then our intuitive sense of a forward-moving time is an illusion that both theories have inadvertently baked into their equations. A theory of everything built on this flipped foundation would not see time as a parameter or a dimension, but as a consequence, an outcome of the universe's quantum gravitational evolution. This could lead to a framework where the smooth spacetime of relativity naturally emerges from the frenetic quantum activity of a more fundamental reality, much like the calm surface of a lake emerges from the chaotic motion of countless water molecules. While deeply speculative, this approach turns a philosophical puzzle into a dynamical one, offering a fresh and potentially fertile path for the next generation of physicists. The true value of the collapsing cosmos may not be in being right, but in forcing us to ask a better question. A radical idea like this can easily spiral into the realm of science fiction. The line between a speculative hypothesis and established fact is dangerously thin, especially when the topic is as mind-bending as the nature of time itself. We have a responsibility to tread carefully, to separate the thrilling possibilities from the well-trodden ground of scientific consensus. The evidence for the Big Bang and the expansion of the universe is not weak. It is overwhelming, built upon decades of meticulous observation, from the cosmic microwave background to the abundance of light elements. These are the pillars of modern cosmology, and they remain standing strong. Presenting an alternative like the collapsing universe is not an attempt to tear those pillars down. It is an exercise in exploring the very edges of the map, where our understanding phrase and new, uncharted territories might lie. The value is not in claiming to have the final answer, but in demonstrating how science grapples with its own mysteries. It is about showing the process of questioning, of daring to ask what if, even when the answer seems settled. This is how knowledge grows. Responsible communication means being transparent about the speculative nature of such ideas. It means clearly stating that this is not the new standard model, but a fascinating thought experiment that highlights the cracks in our current understanding, cracks that future observations may either seal shut or pry wide open. By framing it this way, we do not mislead. Instead, we invite the audience into the real, dynamic, and sometimes messy process of scientific discovery. We foster a sense of wonder about the cosmos while strengthening trust in the careful, evidence-based methods that guide our search for truth. The goal is to inspire curiosity, not to sell a certainty that does not exist. This final thought experiment reveals the ultimate illusion. Picture the entire lifespan of the cosmos laid out before you, not as a movie playing from start to finish, but as a single, complete sculpture. From this outside perspective, you would see the universe contracting, its matter and energy flowing from a vast, dispersed state toward a final, singular point. The entire cosmic story is one of gathering, of a great coming together, but now, step back inside. You are a conscious being embedded within the timeline, experiencing it moment by moment. From your limited vantage point, this grand contraction would look exactly like the expansion we measure. Galaxies would appear to rush away from each other because you are living within the flow of material converging toward a future destination. The cosmic microwave background would cool over time because you are moving away from the intense heat of that final singularity, which exists in your future. Even the relentless increase of entropy in your daily life, the breaking of cups and the fading of stars, would feel perfectly normal. It is the local manifestation of the universe's journey from a disordered future to an ordered past. The difference between the global reality and our local perception is the heart of this radical idea. We are like passengers on a train that is, from a bird's eye view, clearly moving down a mountain, yet from our window the landscape appears to be rising up to meet us. Our senses and our instruments are not broken, They are simply interpreting the universe's true motion through the narrow lens of our own experience. This is a powerful and humbling reminder that our view of the cosmos is not a pure, objective truth. It is a perspective shaped and constrained by our position within the very system we are trying to understand. The universe might be telling us a story, but we are only reading it from the middle of the book, unaware that we might be holding it upside down. We have traveled to the very boundaries of what we can know, guided by a single, radical question. This journey does not end with a definitive answer, but with a renewed sense of wonder. The standard model of the Big Bang, supported by a mountain of evidence, remains our most robust map of cosmic history. Yet, the value of exploring an idea as strange as a collapsing universe is not in proving our map wrong, but in reminding us that the territory itself is infinitely mysterious. It forces us to hold our deepest assumptions up to the light, to scrutinize the very meaning of time, cause, and effect. Whether this hypothesis fades into obscurity or one day finds unexpected support, its true purpose is served by stretching the limits of our imagination. The most profound breakthroughs in science have always begun with a willingness to ask, what if everything we believe is only part of the story? So the next time you find yourself under a clear night sky, look up at those ancient points of light. Consider that the story they tell might be even more incredible than the one we have written. The cosmos is under no obligation to conform to our intuition. What do you think lies beyond the edge of our current understanding? Could the universe truly be a story told backwards? Share your thoughts in the comments and join us next time as we continue to explore the greatest mysteries of space.